Thank you for coming to the talk. So this is my title, Beyond Communications, Codes Offer a Clear Advantage. And CLEAR stands for Computing, Learning, and Recovery. As always, we start with Shannon. We pay homage to his 1948 masterpiece that started the whole revolution of digital communications, and his famous block diagram. And of course, he also pioneered source coding and channel coding, where he introduced the fundamental concepts of entropy and channel capacity that you guys all know. The impact of codes has been felt for decades, starting from source coding, Huffman, Tunstall, arithmetic, Lempel-Ziv, and of course, channel coding, Hamming, Reed-Solomon, LDPCs, Turbo, and Polar. And I'm sure there are others, and that's the QR code of the URL of my page, in case you're interested. I'm going to focus on channel coding for the most part for this talk. Here's a primer on error-correcting codes for all those who are not familiar with them. I don't think there's anyone, but nonetheless, if you have 3 data chunks, x1, x2, x3 to deliver, and you have 4 cabs to deliver them in, and these are your London cabs, of course, and each cab can carry only 1 chunk size data. You know that one of them is going to get delayed because of the fog. And what do? Well, you do the obvious. You do x1, x2, x3, and then you add a parity on the last one, so that if x2 gets delayed, you still can recover x2 by decoding the other. So this is the essence of error-correcting codes. And of course, they have been used extensively in communications and storage, starting from low-density parity-check codes for Wi-Fi, cellular, satellites, Reed-Solomon codes on cloud storage, QR codes, RAID, WiMAX, and more recently, regenerating codes, which are part of the open source Apache Hadoop 2.0. So as a community, we've come a long way. But that's not the purpose of this talk. We want to kind of herald the past, but look ahead to the future. And the future is about big data, inference, and learning, all the buzzwords. So that's what the theme of this talk is going to be. It's about computing, learning, and recovery, and what's the role of codes, and in particular, to speed up these operations. So the theme is codes for speed. So first, I'm going to talk about learning and sparse recovery. That's going to be the first stop. This is joint work with Samir, Simon, and Orhan. So the motivation is that we have, you're given a training data points, x, y. Our goal is to learn, say, a certain rule that explains the labels from the features. This is the standard supervised learning problem. For example, you might have areas and bedrooms as your features, and the house price might be what you want to predict. And you want to understand what is the function. You want to learn the function by given many examples. Questions of interest is how many data points do you need, and how long does it take to compute this? So these are fundamental questions. And also, how robust is it? So if you have perturbations. For example, simple example is if you have linear f, or affine, and problem dimension is just 3, because there are only 3 parameters. That's an easy problem. We know how to do it. However, the actual problem is humongous, right? We don't even know what it is. And it'll at least be polynomial time in the dimension of the problem. So the sample cost is going to be exploding, even polynomial. And you feel pretty exhausted. So what if you could actively choose the training data, and the model has inherently sublinear degrees of freedom? I'll talk about that in a minute, what that means. But essentially, it's going lower than linear, as you can see in this curve here. So we want to see whether we can, if the problem is so structured that the degrees of freedom is sublinear in the ambient dimension, we want to be able to exploit this. So that's the theme of this talk, and you'll see that the sublinear cost will be a pervading theme. Okay, and the potential impact is huge, because there's a lot of applications that can bank on this concept, from MRI, which I will show some examples of, to radio astronomy, sub-Nyquist sampling, IoT, computational imaging, and of course, machine learning. So we'll start with the sparse spectrum theme on sparse graph codes. So let's begin with a polynomial learning exercise, which is really high school level. So you're given a polynomial of degree n-1, capital N-1, and you want to find the coefficients of the polynomial. So how many evaluations do we need? We know from high school algebra that if you have a quadratic, you need 3 points, 3 distinct points. If you have a 7th degree polynomial, you need 8 points. And in general, for n-1 degree, you need n evaluations. But what happens, and what is the connection to how do I do this, or how do I recover? It's very clear that as long as I have distinct points, I have a van der Waals system of equations, and I can solve for, I need to calculate the capital F's, these are the coefficients, and I know the evaluations, the little f of xi's, and I just write the matrix form, and that's a van der Waals matrix, and you can solve. So that's how we do it. And this is, of course, related to the DFT, or actually the inverse DFT. If you pick the points as the roots of unity, the complex roots of unity, equally spaced, you will get exactly the DFT. OK, but we are interested in knowing what happens if the degrees of freedom, which is the number of sparse coefficients, is small. It's sublinear. By sublinear, we mean that k over n goes to 0 as n gets large. So in this example, f of x is, of course, your nth degree polynomial. Say n is 1,000,000, big number. But the sparsity is 200. Only 200 of these million coefficients are non-zero. So how many evaluations do we need, and how fast could you do this? And spoiler alert, it turns out you need only 616 evaluations for this example. So that's a distinct savings in computation time. And I want to explain how I will go through this, but I'm not going to go rigorously through the theorems, more explain the concepts. So, of course, we said that the problem of computing the DFT is the same as finding the sparse coefficients of the polynomials. So this is your formal definition of the k-sparse DFT. You have x of n is, this is your DFT, and the x of k's are the coefficients, the Fourier coefficients. And we assume that the k index is chosen uniformly. All n choose k subsets are equally likely. So that's an assumption we'll be making. And the result is that there is a fast Fourier aliasing-based sparse transform, which I'll talk about, where if k is n to the delta, so delta is my sublinearity parameter, so delta goes between 0 and 1, you can show that, of course, there are many caveats on when it holds, but I'm going to skip those here. I just want to give you an overview. So it uses fewer than 4k samples for delta up to 0.999 or something, essentially the entire range. And most surprisingly, the computation time doesn't depend on n for the noiseless case. So it's just k log k. So, and it's also robust to noise. It has some polylog parameters. I won't go through the details of how you get these numbers. But the key point is note that the number of samples and the time complexity, when you divide by n, goes to 0 as n gets large, so which was our goal. So sublinear time recovery when you have degrees of freedom that are sublinear. So to explain this, I'd rather indulge you in a sort of puzzle. So in India, when we were small, we read a lot of comics, and the comics were full of characters like this. And you have this gold merchant, and he has these gold coins, 100 grams each, and he gives it to his ministers for safekeeping. And so there he did. So he divides them up, and he gives it to them. But there is one of them who's a thief. And he steals an unknown but fixed amount from each of his coins. So this is the puzzle. So you know that he's shaving off some amount of grams from each of the coins that he's given. And your job is to find the thief with the minimum number of weighings. So we've seen many of these types of puzzles. And of course, Sherlock to the rescue. First thing you would do is want to find out how much did the thief steal. So what would you do? You would take one from each of them and find out how much it differs from the baseline. So we'll do a differential calculation, and let's say it's -5. So is 5 below the nominal baseline weight of the coin that you wanted? So you know that the thief stole 5 grams. How do you find the identity of the thief? Well, you take 1 from the first, 2 from the second, 3 from the third, and you have enough identity. You have enough to identify who the thief was. For example, if the differential weight was -20, the thief is number 4, right? So this is the ratio test. You just divide y2 by y1, and that'll tell you the identity of the thief. So the 4th guy is the thief. And so 2 weighings are enough, and the ratio test identifies the location, and of course, you know the values as well. So this example is actually one of the key insights behind all the stuff I'm going to describe in different forms. But if you understand this example, you're done. Okay, so this is kind of the main thing. So it's very simple, is what I'm saying. So, but life is not so easy. There's not just one thief. You can have 4 thieves, and you might have 12 treasurers who are keeping the coins. What do you do then? Well, here are your treasurers. Key ideas are you randomly group the treasurers. That's 1 bin, 2nd bin, 3rd bin, 4th bin. And I'm going to call, if there's more than 1 thief in a bin, we call it a multi-ton. If there's a single bin, a single thief in a bin, like that, that's bin 3 is a singleton. And what do? If there is a single thief, we do the ratio test, and like what we saw on the previous slide, and then we iterate. That's how we would catch the thieves. So for example, I'll start with the singleton bin, because I know how to deal with that. So I know that 2 is a thief. So I get rid of him. That will allow me to kind of identify the 7th guy, because that revealed a new singleton, and so on, right? And before you know it, I find all the thieves. So this is the key idea of essentially peeling. And it's also the same as Gaussian elimination. So it's just made in a cartoon form. So key questions are, how many groups do you need? How do you form these groups? And how do you identify if a group has a single thief? Okay? So these are the key questions. So back to Signals and Systems 101. So this is signal processing intro material, where you have a signal and a spectrum. So here's your signal, and that's your spectrum. We know all about the sampling theorem. If you sample fast enough, you will get the spectrum will be separated from the copies, and you can filter out the middle copy, and you can get the spectrum back. But if you subsample, you will have what's called aliasing, because you have mixing of the frequencies, and you are sort of irreparably damaged. You can never get the original spectrum back. So this is what we have learned, right? So this has told us to avoid aliasing at all cost. Well, the insights I'm going to give have to do with subsampling below the Nyquist rate, meaning daring to go below. But so it will result in aliasing in the frequency domain. But if you're clever about the subsampling patterns, in the sparse case, you will have a good aliasing pattern that looks like a code. And in particular, if you are guided by the Chinese remainder theorem in your subsampling, you will get a sparse graph code. It just comes out. And we use coding theoretic tools then to not only design, but analyze. So the design part is randomized constructions of good sparse graph codes, which the coding theory community has given us. And the analysis will involve tools like density evolution, martingales, and expander graph theory. We won't go into those details, but in some modified form, all these tools can be leveraged and brought to bear here. OK, the main idea, let's give an example. So here's the time domain signal, which is length 20. And in the frequency domain, you have only 5 sparse coefficients. So, and they are in particular in 1, 3, 5, 10, and 13. So what do? I subsample by 5. And these are my measurements. So when I subsample by 5, I have only 4 samples, because 20 divided by 5 is 4. And then I take a short DFT, which is length 4. And let's say that U, the capital U's 0 through 3 are my DFT coefficients. So we know that the aliasing pattern is to take every 5th one, right? And all these, every 5th one adds up to give you the U of 0. That's why you're saving space. Every 5th one is interfering or adding up. And likewise, you'll get for all the bins. So, but they will be spaced apart. So 0, 4, 8, 12, and so on of the first one, 1, 5, 9, the second one, and so on. OK, so what do? Well, if all these time domain samples were dense, then there's nothing you can do. You're screwed. But the hope is, because you're sparse, you might get lucky and actually recover them. And that's what we're going to bank on. So let's say that these were the coefficients. So all the zeros went away. So I have a sparse graph here. And in particular, I can look. The first bin has nobody coming to it, even though it could have had 5 or 4. So we call that a zeroton. This is a multi-ton because it's more than 1. But the other 2 are singletons, right, in this example. So what do? You do exactly what we did in the thief problem. You peel off the singletons. So we'll show that here. OK, but to do that, we remember that in the thief problem, we had 2 measurements, right? One which was all ones and the other which was weighted. Well, you can get weighting in this problem by simply shifting and subsampling. OK, so a shift in the time domain is a phase multiplication in the frequency domain. Right? This is, again, basic concept. So our measurements are U. So I'll call U sub S to be the index for the shifted versions. And in particular, it's the same pattern, except the weights are now multiplied by omega, or W, e to the minus j 2 pi over 20. And note that the weights are distinct for the 5 symbols, and that will allow you to identify which coefficient, if it was a singleton, is the key, is the culprit. So let's put this together. We'll go from right to left, unfortunately. So xn comes to the right. I subsample, take a short DFT, you get U's. Then I shift subsample and take the DFT, you get the US. And this is my pattern. And I've classified them. The blue means it's singleton, red means it's multi-ton, and black means it's zeroton. So, and these are the coefficients. We don't know that these are the coefficients, but we need to identify the values and the locations. And what we could do is, that's a subsampling by 5. We could also, for example, throw in another. We call that a stage. A second stage would be subsampling by 4. And that will form another pattern. And now you will have 5 of these bins, because 5 times 4 is 20. And again, you'll have some classification pattern, depending on who's 0 and who's not. And like that, you can keep going for many stages, depending on how big n is, which is the size of the problem. And you have also identities of zerotons, multitons, and singletons. And so you can just peel away. So in fact, in this example, you start with that singleton that reveals x10. That's going to uncover more singletons, and the thing propagates. And before you know it, you have all of them done. OK, so that's good. So the key is that sparse DFT computation, or sparse polynomial interpolation, is nothing but decoding over sparse graph codes. So this is the insight I wanted to give. Does it always work? No. I mean, I cooked up this example, so it works. So how do you make sure that it works almost always, or with high probability? Meaning, how do you induce a good graph that's going to work? Well, to do that, let's form some analogies to communications, which we all know. So on the right-hand side, we have our DFT problem. And these are this is what I'd call the pruned graph, where the non-zero coefficients are on the left, and the bins are on the right. Well, this is very similar to erasure channels, where you have erased symbols or packets on the left and parity checks on the right. So that's the analogy. But there are some differences. For one thing, in the erasure case, you have your design is well understood because you make the design. Whereas on the right-hand side, the graph is implicit because it's induced by sampling, right, or subsampling. We know that you have n minus k correctly received packets on the left, and you have n minus k non-zero coefficients, or zero coefficients on the right. And you have k erased packets. There are k unknown coefficients. Your peeling decoder recovers the values from coding theory, and peeling decoder here will recover values and locations, but it comes at a cost because you need to pay the cost of the extra measurement. Okay, so what's the deal with the CRT? Well, let's go back to how sparse graph codes work in the communication setting. So again, let's simplify to balls and bins. After all, that's all it is. So these are the balls of the symbols that are erased that you want to recover. And on the right are the constraints. So you throw these balls into these bins. Let's say you throw them uniformly, randomly, degree 2 from the left, where you pick degree 1 for the top stage and degree 1 for the bottom stage. So you randomly throw 2 from the left. And in the Chinese remainder theorem induced graph, which is our problem, that graph is deterministic. Now, this graph is random. This graph is deterministic because I'm always doing either mod 4 or mod 5. So for example, the third ball there will always go to the second bin or the 0th bin, depending on its label. Now, the Chinese remainder theorem comes in because in this example, any number from 0 to 19 is uniquely represented by its remainders, mod 4 and 5. So if you know the remainder mod 4 is 2 and the remainder mod 5 is 0, there's only one label in the range of 0 to 19 that's going to satisfy that, and that is 10. You can check it. So that ball happens to be ball number 10. And so the point is that all graphs on the right are going to be representable by graphs on the left, because this is the ensemble of all random graphs. But what's less clear is that all graphs on the left can be represented by graphs on the right. But because of the Chinese remainder theorem, that's true, because there's a unique label associated with every ball. And in particular, you can assign labels to all of these balls. So the key here is that the graph is deterministic, and you allow the randomness of nature to select the balls, because they're uniformly distributed on the input side. Here, this is too much randomness. You don't need that much. That's kind of what I'm saying. And therefore, the point is that these two graphs ensembles are identical. And this is the key insight behind why you can leverage the tools from standard LDPC with some modifications to analyze the problem that I'm interested in. OK, so, and that's essentially LDPC codes. And the usual toolkit of density evolution, martingales, and expanded graph theory will come into play. So back to our puzzle that I had posed on where I had said, how many samples do you need when n is 1 million and so on? So n is about 1 million here. You have to pick 3 coprime factors. 100, 103, and 107 are coprime, relatively pairwise coprime. And k is 200, I think we said. It turns out that you need about 600 measurements. And how do you do this? You subsample by these factors, shift and subsample, and you take a short DFT. So this is where the complexity comes in, because your DFTs are of order k if your sparsity is k. And so your complexity becomes k log k, since the DFT can be done in n log n for length n. And in particular, we will take 3 of these patterns, and we'll push it through the peeling decoder. So that's the architecture. So in this example, if you count carefully, the number of samples you need turns out to be, there's some overlap, exactly 616. This is where the 616 I told you came from. OK, so this is an upshot of the sort of the density evolution equations that are behind these plots. So this is the theoretical threshold for left degree 3 uniform left degree 3 graph. And the 2 is because of needing 2 measurements for location and value. And on the right, this is the unfolded graph which, from your bipartite graph, you unfold. It's the usual technique of making a tree out of it. And you make the tree out of balls and bins. And you can analyze the density evolution for this case with the degree 3. It's given by this equation. And you want to find mu, the value mu, for which this is going to make sure that you are going to almost surely get what you want, meaning pt plus 1, where p sub t is the fraction of non-zeros that are not recovered, that are still unresolved at time t. So you want pt plus 1 to be less than pt, which is meaning you want to lie to the under this 45-degree line, the black line there. And you plug it into that equation, and you try different values of mu, and you find the value of mu for which it just lies below. It's like similar to exit charts. So in this example here, mu will be 1.23, for which that's the red curve, for which it barely touches the blue line. So it's a purely contractive mapping. So you'll go all the way down to 0. So this is only an average analysis, the tree analysis, and then you have to do some more work, like martingales and expander graphs, which I'm not going to talk about. But this is behind the theory behind this. And in practice, there's a very tight convergence between theory and practice. And for example, if you pick n to be 7.7 million and k equals 400, m is 1248, you plot the curve, it looks pretty close to the red line, right? So, okay, what do we do with noiseless to noisy? So this is noiseless. So this was all pretty easy. The concepts are much clearer in the noiseless case. So we dwelt on that. So these are the stages. And in the noisy case, you have a more difficult problem. But we are going to resort to the philosophy that we will just spend more measurements to make sure that we are very sure about the singletons that we detect. So we want to identify the singletons. In the noiseless case, it was very simple. It just falls out of the ratio. But now you have to do some noise averaging. So you need a lot more of these shifts. And in particular, you need about log n, order log n of them, or a little more than that. And if you do that, you still maintain the philosophy of maintaining the fact that you will have a rich supply of singletons as promised by the sparse graph code. Now you identify them, and then you peel them off. It's like successively peeling off. So that's the philosophy. And we have applied this for MRI. And in MRI, you have acquisition in the what's called K-space or Fourier space. So, and you want the Fourier transform of that will give you the image that you're looking for. So that's the way the MRI works. So it's and if you have sparsity in the image that you are trying to resolve, then you can cut down the acquisition time at the front end, which is the big deal in MRI. You don't want to take too many samples. That's why MRI is costly. Okay, you want to cut down the time. So here's a cartoon simulation of numerical phantoms for the cardiovascular MR. This was courtesy of ETH. And this is a 336 by 323 image. So this is your cardiac cartoon of the cardiac beating up and down. We exploit the temporal difference across different frames of the phantom. So that's where the sparsity is coming from. Across time, you have very few samples. So it's not uniformly distributed, but nonetheless, the thing works. And here is a MATLAB screenshot. This is the sampling pattern. You can see it's very structured. And here is the recovered image in the difference frame. And the screenshot of what's happening. And it's basically perfectly recovers the sequence. But this is a cartoon image because I just want to show that this works. And in this example, the measurements are 35% of the Nyquist rate. But more importantly, I'm interested in, I don't know if you know what that is, but that's the world's first digital camera done by Kodak in '75. May it rest in peace. Kodak is gone. And viewing the photograph, you had to kind of tether it to a big TV monitor, black and white monitor, and view the photograph. That's the way things used to be. Of course, this is not the most state-of-the-art one now, but if you think of the Kannan 2000, you can sort of see, you can frame the picture and see it in the viewfinder. So the hope is that you can actually do a real-time MRI with a viewfinder. So I'm kind of working with some folks in the imaging, in the MRI space on trying to see if you can make this work. So because you can get a pretty crude picture with the viewfinder, you can potentially have the radiologist move the thing around in real time, because this thing is very fast, and maybe identify which picture he wants to really take for his diagnosis. And then he can be more expensive in that computation. So it's like a dual mode. But this is ongoing work. OK, so moving on. So how much time do I have?
15 minutes.
Sorry? 15. Oh, OK. I got to speed up. 20. OK, fine. Speeding up learning and recovery of pseudo-Boolean functions is going to be the next stop on the journey. And this is joint work with Samir, Simon, and Orhan. So the Walsh-Hadamard transform is a close cousin of the Fourier transform, but it's for the Boolean space. And it's given by this formula. Don't worry about it. What it is actually a high-dimensional DFT over the hypercube. So this is for length 8 signal. So you have your 8-point signal. You arrange it in a cube. And you take 2-point DFTs along each dimension. And you will get your WHT. Okay? So that's what it actually means. And the spectrum, the Boolean spectrum, turns out to be sparse in many important machine learning applications like decision trees, regression trees, evolutionary biology, and hypergraph sketching. So I'll give you an example with hypergraph sketching. So what is the WHT? It's useful to look at the polynomial interpretation, just like we did for the DFT. So this is the WHT relation. So the M and K are binary indices. They go 0 and 1, and they're n long because it's n-dimensional. And it's helpful to set -1 to the mi to the variable xi to get a multilinear polynomial. And this is called a pseudo-Boolean function. It goes from -1, the Boolean space, to a real value. So example, n equals 2. You have 4 coefficients. And the terms are 1, x1, x2, and x1, x2. For n equals 3, you'll have up to third-order terms. So you'll have up to x1, x2, x3, and you have 8 coefficients. So there's a one-to-one mapping between the WHT coefficients, which are these capital Fi's, and the evaluations of x at the xi's. Okay? So just like we saw in the other case. So for example, if you want to recover this third-degree polynomial, multinomial, you would have to plug in all possible xi's, take values in plus or minus 1. So you exhaust all possible values, 1s and -1s. There are 2 to the n of them, and in this case, 8 of them. And there are 8 coefficients to be found, and you solve. So this is how you do it. But the sample complexity will be capital N is 2 to the little n. So little n is the number of terms. So again, what if only k out of the n WHT coefficients are non-zero? So in this example, I want to show you have 30 variables, and the number of possible combinations, 2 to the n, is 1 billion. But let's say only 64 of these terms are significant. Then what do? Well, again, it turns out you can do it with about 2,600. OK. So the main result is that you can, so this is the pseudo-Boolean function whose spectrum is k-sparse. The sample complexity, you can make it order little. N is the small dimension. Capital N is 2 to the little n. So it's essentially k log of big N. And computational complexity also is sublinear in n, capital N, because this quantity is smaller than n. And again, you can make it robust to noise. I'm not going to talk about that. And just to show you how the sampling happens, just a very quick pictorial. This is the, as I said, it's equivalent to a high-dimensional Fourier transform over the hypercube. So if you sample along this direction, C0 and C1, then what will alias is actually the cross sections that will alias are the points that are orthogonal to this. So this is also an instance of the projection slice theorem for those who may know that. This is an example of that in action, where if you sample along this direction, C0, C2, C4, and C6 will alias. You'll only get 2 points because you're taking a 2-point WHT, but the aliasing patterns are given by orthogonal projections of this. Likewise, if you turn that way, it'll be these 4, and if you go vertically, it'll be those. So just an example of how the aliasing happens. So let's do an example with hypergraph sketching. A hypergraph is just a generalization of a graph. We won't even worry about it. We'll just worry about graphs for now. So let's say that you frequently bought books are being tracked by Amazon. And you have your, what is the thing? Let me see. Yeah, Discover, Lonely Planet, Discover for London, and Paris are bought together. Okay, so let's say that that's what happens. So you have your books, and S is the number of sale patterns, and X1 and X2 have an edge if they are bought together. Okay, that means that people who bought X1 also bought X2. Likewise, X22 and X23. And X9 and X14. So, but in general, this is going to be a pretty sparse graph compared to all possible combinations you could have, right? And you want to learn those patterns. And in general, you have 2 to the n, or if n is 30, it's, as I said, billion. Now, if you recover all the sale patterns can we do this without logging all the transactions? So it turns out a convenient data structure for doing that is a graph cut. So if you sketch the cuts of the graph instead of doing this, so what's a cut? Well, literally, it's a line, and you count how many edges are crossing the cut. So make everything above the line +1, everything below the line a -1. So 1 through 5 are +1, 6 through 25 are -1. And what do you get? Well, there's no cut, so this cut value is 0. What about there? Well, this cut value is 1, because that line is bisecting X9 and X14. So this would be +1 and -1, and cut value is 1, and so on, right? So you can find this cuts. It turns out you can write the multinomial function of this cut function, and it will be in terms of the edges that are in the graph. So for example, you see that this, don't worry about the coefficients in front of them. It's normalized in a particular way. X1 and X2 are together, X9 and X14 are together, X22 and X23 are together. So basically, the problem of finding the hypergraph, the sparse hypergraph, boils down to finding the coefficients of this sparse polynomial, which is what the WHT does. So that's the connection. And if the number of sales patterns is much smaller than n, and the number of items bought is much less than n, it turns out that you can upper bound how sparse the polynomial will be. It's S2 to the d minus 1. So you subsample the cuts, you recover the hyperedges. So example, 50 books, 2 items per sale, and 250 sales patterns. This is the graph. It's actually very sparse because you can see white through it. Otherwise, you can't even see it. It'll be all black if it was dense. Now, the total number of cut values is 2 to the 50. The sparsity is 500. And turns out in this example, the number of cut queries is about 25,000. Many orders of magnitude less than what you need. And in particular, you carefully pick these subsampling patterns, and you can peel away until you get what you want. OK, so there's a C++ implementation of these things in the GitHub site that I've cited here. And more importantly, this is an exciting development that we have a hardware implementation of the sparse FFT done in collaboration with the Berkeley Wireless Research Center, which does the chips, based on my student talking to the other student, and it was nicely done. And in particular, they were doing it for detection of heavy hitters in IoT or spectrum sensing. So in the Wi-Fi band, like a 2 gigahertz band, we wanted to find, there are just a few heavy users, and you want to find out in which bands they are. And so it was used for that application. And the interesting thing is that the analysis time to find this, the acquisition time to find these bands was in SATA real time, because it's in the orders of tens of microseconds, which is much faster than anything that they can do now, because of the sparsity of the spectrum. So this is something that is going on. OK, so taking a step back, what we have shown is that there is this peeling-based turbo engine, and there is a sparse graph code that is dispersing these coefficients or these values, or these sparse objects. And the individual guys are just determining or identifying whether I have an easy problem or not, solving them if they can, and returning it back to the main engine. And that'll create, if you cannot, you say, I can't deal with this. If you can, you do it. And that's how the peeling thing works. So it's a solve with trivial sub-engine. And in particular, I'm not going to go through the details, but you can use this philosophy to do a whole bunch of problems, including neighbor discovery for IoT using group testing, sub-Nyquist sampling theory, compressed sensing, sparse mixed linear regression, and compressive phase retrieval. So all of these problems can be put into this framework, but you have to be clever about how you do the identification. Okay? That's the only trick. The sparse graph is common. That's going to be the main engine. But identifying whether you have a singleton or not, that will need problem-specific details. Okay? And I don't know if I'll have time for this. I'll just go very fast through this. But again, in the compressed sensing problem, you have y equals ax plus noise. The measurement system A is free to design. People typically make them IID Gaussian, and you can get the minimal number of coefficients. Our method will involve using a coding matrix row 10-third with the sensing matrix. The sensing matrix is to identify the singletons, and this is to disperse the coefficients so that you'll have lots of singletons. And in particular, you'll have a structure like that, and you can show that you can do this in order k time and order k computations in the noiseless case, and k log n and k log n for, again, sublinear time. So convex methods will need non-sublinear time. They will be superlinear. Another interesting application is sparse mixed linear regression. I just mentioned that. So this is a generalization of compressed sensing. So you have, let's say in this example, you have 3 beta vectors. You want to identify them. And, but at any given time, you're getting a random measurement from one of them. You don't know which, and added with noise. And from these yi's, you want to estimate the beta i's. So it's a problem, and there are many applications. I won't go through the details. But the challenge is that you don't know which beta L is associated with each measurement. So there are L classes, capital L. So it's a simultaneous recovery and demixing. You need to both separate them and find their values. And it turns out that you can do this in, again, order k time as long as the number of classes is order 1. That is, you don't have scaling in this. Number of classes is fixed, say 2 or 3 or 10. Noiseless case will be order k, and the noisy case will be k polylog n. Again, it's sublinear in capital N. And I think I will skip the phase retrieval, but just highlight the fact that all of these will require very specialized tests in the identification phase. And in particular, if you do that, problem-specific subcode for doing the identification, along with a turbo engine, which is the sparse graph code, will uncover all of this. OK, finally, in whatever time I have left, 10 minutes, hopefully, or even less, we will talk about speeding up distributed computing on the cloud, which is the third stop on the way. This is with a lot of students and former students, now professors, Ramtin, Kangwook, Dimitris, Orhan, Vipul, and Tavor. So there's a new kind of noise on the cloud. We call it system noise. It's due to all these features. It's not AWGN, but just as harmful because of all these problems. So you have network failures, maintenance, and network bottlenecks. So system noise, the latency variation, you must have noticed that sometimes when you compute, it stalls, and other times it goes fast. So there's a lot of variation in the latency. And we'll just take an example of matrix vector multiplication, which forms kind of an atomic component to many of these operations. And if you want to multiply A by B, you divide A. You have 3 workers. This is how it happens on the cloud. So you give A1 to the first, A2 to the second, A3 to the third. Each of them does their multiplication, and then you get your answer, Y1, Y2, Y3. So that's what we do. But because of the latency issues, you will get Y1 and Y3 quickly, and Y2 will take its time. And so that is causing trouble. And that's what we call stragglers. And there are many reasons for these stragglers. And Jeff Dean has said it's infeasible to eliminate all latency variability. So it must be, since Jeff Dean said it, right? So in particular, things like data locality, shared resources, and network latency contribute to the straggling problem. And it turns out that the straggler problem can be severe in terms of the slowest worker can be often 6 times slower than the average. So, and this is from Chen from Google Brain. So, and there are other experimental validations of this. So what do we do? Of course, there's a great opportunity to have codes come to the rescue. And now instead of dividing A into 3 pieces, A1, A2, A3, I'll divide it into 2 pieces, call them A1 prime and A2 prime. So A1 prime is bigger than A1. It's 50% bigger. And I'll form a third one, A3 prime, which is just A1 prime plus A2 prime. And that's what I'll do. So but of course, note I'm computing more, but because of the code, I'm more resistant to stragglers. In particular, if the first 2 come in, any 2, I'm done. And so I can compute Y2 prime from that. And that's the basic idea of this coded computing. And if you were to generalize this to n workers and k subtasks, and if the compute time was shifted exponential, which is constant plus exponential, and of course, the average compute time will be proportional to the length of what you're doing. So you do penalize the guy who's computing more. It turns out that the replication case, which is what the current standard is, doesn't buy you anything because of the coupon collector effect when you do repetition. But the coded solution will give you a log n factor gains in the computation time. And that's reflected here. 1 over n, the k star is the optimal value for which the code works. So basically, what's the right size, how to size it up. And on actual simulations on the Amazon AWS, there's 30% speed up compared to uncoded and replicated jobs. OK, so just the big picture is that on the left, we've shown kind of what's the current operation going on in the sort of computer science world. What they do is typically, in the systems people, they detect something is straggling and they relaunch the job. This is the most famous thing that they do. And they replicate. And since we know codes, we can come back and say, hey, you're just doing a feedback code, or you're just doing a repetition code. But we have other tools that they don't do. So like MDS codes, sparse graph codes, codes for caching, all these things, they don't have counterparts on the left-hand side. And the applications are many, from distributed linear regression, nonlinear function computation. There's also a trade-off between computation and communication. And that can be, data shuffling can be done using network coding. So there's a lot of these works. And in particular, I'll just focus on the fact that what I said if you use matrix multiplication, linear regression, and matrix completion as 3 typical examples of jobs you might do, you get sizable reductions in the latency of the order of 30%. So there's some value in it. There's some impact. And it's a very vibrant area right now. I'm sure the ISIT coming up will have even more to add to this. But this is just a laundry list. But I want to talk about something that I think I'm excited about, that I want to share. So maybe this will determine where we go. A decade ago, cloud servers were abstracted away from physical servers because you were computing on the cloud. It's somewhere there, but it's as if it was here, but I don't care. But the future appears to be, I'm not saying this with definiteness, but it appears to be that what's called serverless computing. It doesn't mean there's no servers, but it abstracts away the need for cloud servers as well. Okay, so what does that mean? Well, this came out. There's something called function as a service. This is the new acronym, FaaS, like software as a service is the current buzzword for SaaS. Now it's FaaS. So basically, you run your function somewhere, I don't care where, and the platforms are AWS Lambda, Google Cloud Functions, et cetera. Why serverless? For the simple reason that it's a simple abstraction for the user. Right now, you need to be an expert to use clouds, to do computing on the cloud. You need to have an expert. This is for dummies. So undergrads and you and I, we can all do this. If you're not qualified to program on the cloud. Because it's a simple abstraction, and the cluster management issues are hidden from you. And it's tremendous scale. You have thousands, tens of thousands of machines available in a very short time period, but they're ephemeral in that they will expire in something like 5 minutes. You use it or you lose it, okay? And you can pay as you go along. So economically, it's a much better model in which to do compute. So there's a lot of interest from the cloud computing community. So this is kind of where the future is headed. And the rationale for this is given by this work, Cloud Programming Simplified, a Berkeley view on serverless computing. So how it works is your laptop is kind of the server. So that's you, the user. So you write a function, and the folks in Rice Lab, which is the lab in Berkeley that we collaborate with, have written a Python platform to run on top of the serverless computing. So for example, you would download the function and the data. These machines are really dumb things. They just have some memory attached to them, and then they have to go fetch the data from the main memory, which is S3, and then they'll have a program to execute. And then they do that, and then they go back to sleep. So this is how the abstraction is. And it's hidden from the user. And you invoke these Lambda machines. So AWS Lambda are these small machines. And then after the function is done, you have to keep polling the main memory S3 for the results to see if your answer is done. So that's the abstraction. This didn't come out very well, but the snapshot is that you can have up to, there's a lot of stragglers here, okay? So basically, this is for 99%. This Jonas et al. Is occupy the cloud for distributed computing for the masses. But if you do this in a typical setting, you will see that there are lots of stragglers because these machines, you can never predict when they will be done. There's a lot of network latency. But the scale is what interests me, because that's when the stragglers are going to be in the multitudes. But just as a word of caution, we have to be careful about what we are optimizing for, at least on this platform. Again, the master encoding and decoding is your laptop. And the processors are the workers in the middle, the Lambda machines. Note that you have an encoding time. You have a distribution time where the data has to be fed to the processors. So the I/O, the memory between the processors and the master are going to be one of the big bottlenecks. And then there's a compute time for the function to get done. And then there's also a decoding time if there are stragglers and you want to do this. But what are we optimizing? So let's think of matrix multiplication as a black box. Word of caution is that if you use a Reed-Solomon code or something, that only targets the computational aspect of this complete sum. And oftentimes, that is not going to win. The end-to-end latency is not given by the best code. And so there's some sort of optimization involved in what code you want to pick. And you need to scale in the context of this platform to multitudes of stragglers. And also, these are real-valued computations. So you want a code that will be amenable to that. So Reed-Solomon codes are not very friendly for that. So we found that product codes are a good trade-off that offer near MDS with local encoding and decoding. So that's what we have embraced. So there's a lot of literature on product codes and generalized LDPC codes and their connections. But you can imagine that if you just add a parity on, say, the A and the B, you want to multiply A and B, you add an extra parity on B and an extra parity on A. That induces a product structure with only one parity on the corner. And you get near MDSness, low encoding and decoding cost, and it's parallelizable. And you can also do n-dimensional product code. So here's 2D and 3D. And product code decoding is exactly the peeling we have seen before, because the constituent codes are given there. Each row and each column has a constituent code. And you just make sure, as long as you can decode it, you will peel it away. And an interesting result is, this is a connection to generalized LDPC codes, is that you are almost MDS in that you can wait for almost n minus k, exactly k. It's slightly smaller because of this ratio eta of dr, similar to the thresholds we saw earlier. And it turns out that the r equal to 1, d equal to 3, which is A single parity at dimension 3 gives you the best results. It's the smallest time. So you can tolerate almost the minimum amount, but it wins in terms of the sum of all these costs. OK, so very quickly to wrap up. Oh, my plots didn't come out. That's too bad. But it turns out that you can use a couple of applications. We've tried them on a kernel ridge regression using conjugate gradient on AWS Lambda. And 0.4 million examples and 400 workers. The key is that you have to repeatedly solve for k plus lambda I x equals y. Lambda is a regularization parameter. And you initialize this, and then you go through this loop until you're done. But when you repeatedly, so k plus lambda I is a one-time fixed cost, and x is keeping on changing because you're keeping on iterating on that. And so each iteration, you have stragglers, you have wins, and it turns out, I don't remember the details, but you have about 40, 50% gains in the total completion time. Oh, there it is. OK, I didn't lose it. OK, so yeah, it's about 44.5%. This is for every iteration. This is coded computing is on the blue side, and on the red side is the what's called the speculative execution. That is, you wait and see whether you want to relaunch the job, which is a heuristic. So, and finally, another example is PageRank or Twitter recommendations, which is, as you know, important business. So if you want to solve, for example, the maximum eigenvector, you have to repeatedly do bk plus 1 equals abk, the normalization factor. And since you want to keep doing this, every iteration, you're going to get some gains. And so overall, you can get up to 50% savings. Yeah, so basically, in this platform, you took 1 hour, 6 minutes less time in this run. So it's pretty substantial. OK, so to conclude, I wanted to offer a view of codes from a different vantage point for computing, learning, and recovery. On the computation side, we have straggler proofing distributed computing, which is on the cloud. And for learning and recovery, the sparse graph codes-based peeling core with verification test properly chosen can take you a long way. So with that, let me entertain questions.